In our study of rational functions so far, we've seen domain, we've talked about poles, and in the last video we talked about how poles can either be a whole or a vertical asymptote. And I mentioned, if you were paying close attention, that there's a second type of asymptote in this course, a horizontal asymptote. And so that's what this video is going to focus on, is horizontal asymptotes and how that connects to behavior of the rational function. We will return to vertical asymptotes and in particular figuring out, does it go up or down on each side later. But for now, I want to talk about the other type and of asymptote. Okay, so horizontal asymptote. Okay, it's another line. Okay, it's a line y equals d. So graphically, when we look at this thing, okay, we're going to see here's a value of d. It's going to be a horizontal line. Okay, and now let's go through the rest of the definition of the function as approaches positive or negative infinity. So, okay, so it's a line that the function approaches as x approaches positive or negative infinity. So as we extend away from the origin, I'll give you an example, okay? As we extend away from the origin, we are going to hug this line, okay? But notice that near the origin, we're nowhere close, okay? As we extend away, we get close to this horizontal asymptote, okay? And so when we formally talk about this as mathematicians, we say that as x goes to infinity, as x gets large positively, actually you could say positively or negatively, ideally. Sometimes it's only one directional. We would say that the y value, or f of x, which is the y value, is going to approach whatever our horizontal asymptote value is. Okay, so we on the other side here, we could see something happening like this. Okay, we could approach the horizontal asymptote from above or below. I don't know which one, but bottom line is, as I extend away from the origin, I approach this line. Okay, now that's the concept from a graphical and notation perspective. Okay, algebra, it looks scary. Okay, it really isn't too bad. Okay, so remember that when we're talking about asymptotes here, we're talking about them in the context of a rational function, which is a polynomial over a polynomial. Okay, and so we have these polynomials written out in general form. Okay, and I'm going to pick off those leading terms. Okay, a sub n x to the n and b sub m x to the m. Okay, and so p is degree n, q is degree n. So n is the degree of the numerator, m is the degree of the denominator. And then we have the following rules. Okay, n is numerator, m is denominator. So if the numerator degree is smaller than the denominator, we get a horizontal asymptote at the x-axis, y equals 0. Okay, if the numerator is larger in degree than the denominator, no horizontal. I purposely skipped over the second one. And then the other thing is that if they are equal, so if the powers are the same, okay, what I'm going to do is take the leading coefficients in ratio. A sub n over b sub m, so leading coefficients in ratio. Okay, let's see that in practice. Okay, number one, find the horizontal asymptotes. Okay, so I need to look at the leading terms. Here's the leading term for the numerator, and the denominator has leading term 2x squared. Okay, so here I'm going to say n is 1, it's the degree on the leading term. M is 2, so I'm in the case where n is less than m, so that means I have a horizontal asymptote at y equals 0. Okay. For our running example, where we were talking about poles and holes and vertical asymptotes, okay, we look at the leading coefficients in the numerator, and denominator is actually that second term, degree 2 term, right? So now as I look at n, the numerator degree, that's 2. m is also 2. That's the degree of the denominator. So then that means when the degrees are the same, we would have a horizontal asymptote at y is equal to the leading coefficients. Here in the numerator, it is 1. Denominator, it is -1. So in all, I would have a horizontal asymptote at y is equal to -1. Okay. Now number 3, instead of giving the function algebraically, I gave it to you graphically. And so we're wondering, what is the horizontal asymptote here? And so I look at it, and again, horizontal asymptote is long-term behavior away from 0. What is it hugging? Okay. As I look here, as I look away from the origin, okay, I'm not looking anywhere near the origin, it looks like I'm here and here, right? Which, if I sketch this carefully, appears to be this line, right? And that appears to be my horizontal asymptote. So if I look and count that up, I think that's 4. So I'm going to say HA at y is equal to 4, okay? Because again, I'm not concerned about behavior near 0, it's away from 0, long-term behavior, okay? So that's horizontal asymptotes. Now, in discussing horizontal asymptotes, I've repeatedly mentioned that this is indicating behavior away from the origin, long-term behavior, right? And so when we work with horizontal asymptotes locally, and I'm thinking, when I say locally, I mean for small values of x, for stuff near the origin, weird stuff can happen. And one of those weird things is you can cross a horizontal asymptote for values close to the origin. Okay, that's the key phrase. 0, 5, maybe 10, generally not, but maybe 10. But anything beyond that, really you need to start approaching your horizontal asymptote quickly. Okay, and this makes sense because, and again, asymptotes are indicating long-term behavior away from 0. Okay, now I'm going to propose that you can't cross a vertical asymptote, and I want you to think about this and justify to yourself why that is a true statement, and then come back to class with the answer, okay? Now, computationally, how do you figure out if it crosses the horizontal asymptote? Well, it's an equation line, right? Y equals D, okay? So if you wanted to figure out if it did, let's do our running example. So we do x squared minus 4 over 2x minus 1, or minus x squared, right? That was our function, and we found that the horizontal asymptote was -1. Okay, we'd have to set it equal to that horizontal asymptote. So this is your HA, okay? And then just solve for x. So I'd have to, multiply both sides by x squared, or 2x minus 4, or sorry, 2x minus x squared. So multiply that over -1 times 2x minus x squared. And I'm not going to continue with the arithmetic, but you certainly can. I believe you're going to get that it does cross. Yeah, actually, the arithmetic will show that it does cross. So more on that soon. But you can go ahead and find maybe an x value where it does, where it would cross the horizontal asymptote. And it should be a small value of x, okay? But again, big takeaways from this video is the other type of asymptote that we have is a horizontal asymptote, indicating long-term behavior of the function as we go away from the origin horizontally. And so notationally, we're going to see as x goes to plus or minus infinity, y approaches whatever the horizontal asymptote value is. And then graphically, we see something like this, right? And algebraically, we have these sets of rules, okay? Comparing degree of the numerator to degree of the denominator, and then figuring out which case we're in, all right? So more practice on this coming up for you, but for now, we will start assembling all the other pieces of the puzzle as soon as we finalize our understanding of vertical asymptotes.